We've lost the first minute, but we will continue for this presentation. Meanwhile, eigenvectors represent the rotation of the axis toward the direction of maximum dispersion, as we said before. So the assumptions.
Could you please share again? Again, thank you.
Sorry. Okay. Okay. So the assumption and the credibility condition in a PCA. So to perform a PCA, we should have the regularity of the matrix. So the matrix should not contain missing data, and you have to avoid outliers, because as we have seen, outliers will be kept immediately from the PCA. If you have a cloud of points in the center and an outlier in another position, the first axis intersect this outlier. So it is better to avoid outlier. But PCA is also used to identify outliers in a distribution of in a data set. The second condition is the normality. So single variable should be normally distributed, but above all, the multivariate normality should be considered. This is the procedure of the PCA. I'm sorry, but this is in Italian, but we do not enter into detail with the procedure, but we will see in particular which information is obtained from a PCA. So the first important information is the percentage of explained variance by each axis. And this is derived, as we said, from the eigenvalues from this formula. So we have the PC, first, second, third, etc., the eigenvalue, and this is the percentage of explained variance, where 43% is 2.6 divided by the sum of all the eigenvalues percent. So the first axis absorbed the 43% of the total variance, we could say. The scree test or scree plot is proposed by Cappell in 1966. Is a graphical observation which allowed you to observe when the most of the variance is absorbed. So when this curve changed drastically the angular coefficient, you can stop here maintaining most of the information. So in this specific case, you need only 3 axis to absorb, let's see, to lose around 12% of the variance. The second information provided by a PCA is the scores. The scores are the values of the coordinates in the new roto-translated space. So once we have positioned the new axis, we have the new scores, so the new coordinates of each point. Here we have a plot where in the first axis there is the first PC, principal component, with 43.6% of explained variance. This is the second axis, 29.1% of explained variance. And here is where the observations are positioned. This is the graphical report, and this is the numeric report. So for each of the observation, we have the coordinates on the different axes. Oh, sorry. The third information is about, of course, the loadings. So before we have seen the rows, so the observation. Now, sorry. So the scores are information related to observations. The loadings are observations, we could say, the contribution of each variable on each axis. So here, for example, on the first axis, we have the 0.57, so value for this variable that is positive and high contribute. And also positive and high contribute is from this variable B, and also from the variable peso, that is weight. While a negative and important contribute from the negative side is given by this variable A. While on the first axis, H frutto and F max return a lower contribution. So let's turn to our screen. Okay. So let's imagine that at the beginning of our ordination, the points are positioned such as a Big Bang. After a certain point, so depending from the variables, they positioned in some way. Let's imagine let's figure out the example that we made before. So here we have a spot, and here we have a disk. But why here is a disk and here is a spot? Because the variables, so the column, as vectors, try to push the ordination in that way. So some variables have a higher force on the first axis, so to discriminate the spot from the disk, and other one works much more on the second axis, and so their forces on the second axis are higher. This is the, let's say, graphical meaning of the loadings.
Corrado, sorry, there is a problem because we cannot see the presentation.
No, I'm not showing.
Okay, okay.
I'm just showing myself now.
Okay.
Okay.
Because I'm reading the chat, so sorry for the interruption.
Okay, no problem. Now we can come back to the presentation. So I gesture the meaning of the loadings. So the loadings is the contribute of each variable on each axis. This is the best graphical representation of a PCA. In this graph, this plot is named B plot. In this plot, we can see the first information, that is the explained variance. So 43.6% for PC1 and this other percentage for PC2. The coordinates, so the scores, the black dots with the labels here, and the loadings represented as vectors. These vectors are adimensional, so the length of the vector is comparable with the other vectors, but they do not stay in the same space. So the length of each vectors could be the half of this, but all the half. So weight is not here, could be here, but H frutto is also longer or shorter. It's just a graphical representation. So here we can observe that the points that are here in that part, so in the negative side of the PC1, so pomodorino, most of all pomodorino, are characterized by higher values of A and lower values of peso, L, and B. On the other side, Ins Romana, there is a salad, have higher weight L and B and lower values of A. On the second axis, we can observe that here Nectarina, most of all Nectarina, has higher values of Fmax and H frutto, and lower values here for Pomodorino and Susina of Fmax and H frutto, and higher values of B. This is a graphical representation obtained by specific software, in particular PAST. We will go in deep with PAST in the next half an hour. But it is possible to build a B-plot also in Excel. We will see this practically. We have to use some tricks in most of all when we have to plot the vectors of the loadings, but we will see this in practice. As we said before, PCA requires quantitative variables, and these variables should be multivariate, normally distributed. So if we have matrices with containing too many zeros, the distribution is of course non-normal, and so we could not use a PCA to observe this matrix. Okay. How to measure the multivariate normality? It is not a common practice to measure multivariate normality. There are tools, in particular PAST, the software PAST that we will use, have a specific tool for the test of multivariate normality. But be careful, because this test is very restricted. So with large data set, often it happens that the distribution appears as non-normal. There are other much more stable tests, but you have to use different software packages such as MATLAB or R. So if there are questions, please stop me and feel free to intervene whenever. Okay, but what to do if the multivariate normality is significant, or if we have a matrix with many zeros? Okay, we could not use a PCA, but there are valid alternatives, such as the principal coordinates analysis. We will see this analysis later. There are 4 different versions of the PCA. In particular, for standardized or non-standardized data, and for centered and non-centered data. In PAST, we will see that we have 2 options, so only for standardized or non-standardized data. And the result could be very, very different. Here is the natural plot, and here is the standardized or non-standardized plot of the data. So this is the original one, that is the same here, and this is the same but with standardized or centered data. My suggestion is to always standardize data in order to avoid the effect due to the magnitude of variables. So we can have variables having a magnitude of thousands with variables having magnitude of 0 0.001. And so to exclude this magnitude effect is preferred to standardized data. In past is a simple click to standardize. So how to represent data? In the example before, we have seen a B-plot, so a representation with dots and labels. Here we have a very easy representation. This is not a B-plot, but a simple score and PC axis variance plot using symbols, different symbols. Or you can use different colors and different letters or colors, but be careful, please never forget to indicate the variance explained by each matrix. This is a quite common error in the publication that often I also review it. But sometimes you can, especially if you have many data, it is possible to represent data as centroid. So the centroids are the mean of a group. It is better to represent the centroid with a standard deviation or standard error, so a cursor representing also the variability of the plots. So instead of thousands of small points, you can represent the centroid, but please use also a dispersion graphical for the graphical visualization. Here is represented also, this is a shape of a fish that is different from this side and this side. In this other example, the dispersion index is represented with the size of these poles. Also here, the explained variants are missing. This is an hybrid solution with all the observation, so all the scores of the observation, together with this black one. This is the centroid, and also the representation with the ellipses that we see. So this is not a PCA, but is a similar graphical representation. When you have few groups, 2, 3, 4 groups, you can represent also the convex halves, so the perimeter, including all the points of a group, or the ellipses. The ellipses, be careful that have the 95% confidence interval, so has a statistical meaning, a precise statistical meaning. So please do not trace by hand the ellipses, because this is wrong. So after conducting a PCA, of course, the most important way of representing a PCA is important also to interpret the data. And so, of course, you have to observe the meaning of a distribution. We will see in the next 4 slides different kind of distributions inside a PCA. So it could be something that potentially could happen to all of you. Here we have the simultaneous sorting of 27 measures and 6 environmental variables. So we have 27 rows and 6 columns, obtained by applying the analysis of the PCA to the matrix of coefficient of correlation between variables. So we have cliff transept, sandy transept, intermediate environment. The first axis explains 72 of the total variance, so this is the much more important. The second one, 24. So it's quite 100% using the first two axes. So here we can see a gradient shape. So a gradient that goes from this sandy transept here to the intermediate to the cliff transept here. And why this is positioned in this way? Because in this part we have the sand, percentage of sand here higher, of course, in the sandy transept here, and also the presence of species is higher here. On the other side, in the cliff transept, is characterized by percentage of rocks, of course, the transparency of the water, the richness, and also the pendants, can't remember in English, however, by these four variables here. This is another kind of distribution of data inside the PCA. So we have an example of groupings. Here we can observe 12 sampling stations and 4 insect taxa detected along a forest transept. Here we can observe 3 groups, but please remember that PCA is not a clustering method. It's used from other statistics as an intermediate to perform a classification, but is not a classification tool. You can observe that there are some observations that cluster together, we can say. And so here we have the taxa B and C here, taxa D here, taxa A here, this is the variable, and here we have the different soils, other soils, clay soils, sandy soils, and soils rich of organic matter. What is missing here? Of course, the percentage of explained variance. Overlapping distributions. Here we have 77 individuals belonging to the same, this is bird species, Passeriformes is birds, obtained by morphometric variables. So with the white one is mountain environment, and the other one is, I can't remember, but maybe plain environments here. So we can see that here there is a trend on the first axis here, where in the negative side we have the mountain environment birds, and in the other side the plain environment. But the two distributions are quite overlapped. I suppose that observing this data, because I remembered you that a PCA is an ordination technique, so it's a way of observing your data. So from this graph, I can observe that there is a trend, that there is a tendency of between mountain environment birds and plain environment ones. I could say that using a proper classification technique, maybe these two classes will be well separated. This is the last distribution. This is a random distribution. So you can see that all the blue dots and the black squares are mixed one to another. So are not distinguishable. So even if we apply a discrimination technique, maybe we will not able to separate this group. Maybe on the third axis that could be something, but it is much more difficult than the previous distribution. So now we will go to work on past. On past, we have two options. So we have the option of use the variance variance and covariance matrix. So the matrix we use the same units of the original matrix, and the correlation matrix which standardized the matrix. I suggest to ever use the correlation matrix, so to ever standardize your data, because in any case, standardizing data do not alter the configuration, and is better than the original kind of information that you input. So let's go to the first exercise. So inside your folder, you will find a PDF and some Excel file. So please open exercise 1. Exercise 1. Here we are. So this is an example from the percentage of employees in different industrial sectors in the European countries on 1979. Okay, so here we have different sectors: agriculture, mining, energetic, construction, etc., etc. So we would like to verify the employment structure if it is linked to different economic, political systems in Europe in that period, so 1979. Okay, so now you have to open the software past. A brief explaining of past. Past is an executable in this version. This is the version 2. Is an executable which do not require to be installed. So you can only click on this exe file and it should work. There are other more recent versions, so the version 3 and version 4, but be careful, because in some cases the algorithms are not verified. So it happens to me that some algorithms are not right. So this is a stable version. You can try the other one, but please verify the results you obtained. So this is a sort of a data sheet. It's quite similar. Sorry, it's quite similar to Excel. We have only to remember something. Where is past? Okay. 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 No. Okay. So the first thing is that if we want to paste the labels, we have here to click Edit Labels. We can copy all the data set with the labels of rows and columns, put here, paste, Control D. C here and Control V here. Okay. And then click again on Edit Labels. Here we are ready to process this data set. If you have problems or you want that I repeat something, please interrupt me. Okay. Now, a rule for past is that past elaborates the columns that you evidence. So to evidence all the data set, you have to click here. So click here, then go to the menu Multivar. You can see that there are a lot. This is a very, very beautiful and of course open source software. So for the simple statistics, it's valid. We will see something tomorrow, but also for some multivariate statistics, the one it is necessary for this course. So here in the multivariate menu, you have the principal components. Let's see. This is the first information. So you remember that a PCA returns you three kinds of information. The first one is the explained variance. Here we are, eigenvalue and explained variance. The second one is the coordinates, so the scores, the new coordinates, so the scores. And the third one is the loadings, so the contribute of the variables. Here is the first information. Here we have the possibility to standardize the matrix. The default value is the non-standardized option. And using the correlation, you can standardize the matrix. Okay. And here we can observe the scatter plot. Okay. So we have the first component here, the second component here, and here is the scores, so the coordinates of the observation. We can simply label these scores. So this is the observation, so the rows, the different countries here. And also observe the bplot. Simply click on bplot here. And so this is the loadings. Unfortunately, to put the explained variance, you have to do it by yourself. So click here and modify the label component one. I can't remember 74.5. I can't remember. Just to show you. And the second one is around 20.1. The correct number is here. Here. So 38.7 and 23.7. Okay. So
sorry, may I ask you an information regarding the copy paste in the sheet, because when I try to copy the set of data, I do not succeed in inserting the labeling in the first row and the data in the first column, but it remains the previous one. How can I correctly insert? I have to.
So my suggestion is to do it in that way. So start it over. File, new.
Okay.
Okay. So copy from Excel here.
Okay.
Edit labels.
Edit labels.
You have to click here to edit labels. And you have to put in the crossing here. So in this part and paste. Control V. And then again, edit labels.
Edit labels. Okay. Okay. Edit labels.
Paste.
And paste. Okay.
And then again, edit labels.
Edit labels again. Ah, okay.
Okay, it works.
Thank you so much.
You're welcome. So now to start the analysis, please remember that you have to select all the column or the columns that you want to process. So in this case, all. So you have to click here at the crossing. And then the menu is multivar, principal components. Here you can see the percentage of explained variance, correlation, so we standardize the matrix, view scatter. We were manually modifying the axis, inserting the percentage of variance here. So just clicking inside and modifying here the labels. So component 1 or PC1, we can also modify, writing PC1. So this is 38.7%. And here PC2 23.7%. Okay. Okay, here we are. Maybe we can also enlarge the labels so that is visible also by you. Okay, so let's see this this ordination, this graph. So first of all, I unselect the B-plot. So let's see the countries here. Please remember that we are observing the situation at 1979. So there was the war in Germany, and there was the Soviet bloc and the Eastern bloc, Western bloc, and so we have to observe preliminary something. So here we can observe that Turkey, Yugoslavia, Greece, Romania, here we have some countries from the East, the Soviet East, Hungary, Czechoslovakia, Eastern Germany, and here we have the Western, Northwestern maybe, so Sweden, Denmark, Netherlands, Belgium, Norway, France, here. Where is Italy? Here is Italy, okay. But why these countries are positioned in that way? Remember when I told you about the vectors? So this kind of forces from one side or another side. And here we can introduce the plots, so the loadings. Here, Turkey is here because has a lot of employees in agriculture, and also Yugoslavia, Greece, and Romania. So they are, in that period, they were rural countries. Here we have mining countries here, and here is linked to finance. Okay, this is the meaning. Let's try to observe here we can see the numbers here. This is the coordinates on the different axes. We can copy and paste in Excel to make the graph by ourselves. Okay, we can plot PC1 against PC3, for example, or PC2 against PC3, etc., etc. Okay, so let's come back to PC1 against PC2. Okay, let's close this. This is the loadings. We can observe not on the graph as a B-plot, but on this kind of representation with histograms. You remember that on the first axis, on the negative side, we had agriculture. So in the country with the lower coordinates on the first, on negative coordinates on the first axis, who had a lot of agriculture. We can also observe the original values. So if we see, where is Turkey? Here, 66% in agriculture. There were also Greece, 41%. Romania, I remember. Romania, where is, okay, 34%. Let's try to see if we do not standardize the data, what happens. So let's see the countries. So in the first axis, almost nothing changes. So we have always Turkey, Yugoslavia, Greece, of course. But we have Switzerland with East Germany and Czechoslovakia. And this could be a problem. Here we have always Norway with Netherlands, Sweden, and Denmark, but Switzerland with East Germany and Czechoslovakia could be a problem. Let's see why. So the plot. Agriculture is the first, the most important variable on the first axis, of course, but on the second axis, the manufacturing variable have a greater importance if this is not standardized. Let's see why. So man here are always higher values, but very, very similar among them. So here we have East Germany and Switzerland. Switzerland 37 and East Germany, where is it? Here, 41. Of course, they are higher, but not so different if we consider if we standardize data. So it is much more true representation standardizing data than not standardizing them. Okay. Okay. Everything is okay. We passed with this example. No question about that. No. Okay. So I propose you some other examples on PCA. We will work mainly on PCA because it is the most important technique. The other technique we will observe, of course, other techniques, but I prefer to go in deep with PCA because it's wider used. So let's see the 5 ordination techniques. So, okay, ordination. Okay, the Excel file. It's opening, okay. Here we are. And which is the PCA horticultural 70 measures. Here is the example. So here we have different horticultural species. So this is a salad, 2 kinds of salad. This is peach, nectarine and peach. Small tomato. Susina is, don't know in English. And zucchini. Yeah. And these 6 variables, L, A, and B, are luminance, are related with color. L, and A, and B, CHILAB color coordinates. Dimension, so the age, the height of the fruit. The penetrometric force, F max, and the weight. Okay. we can copy this data set here with the labels. Okay. We can go to past. Of course, you can save this data set, save as, past, save the data set dot dat. Or in this case, I open a new sheet. So please remember, edit labels, put at the crossing here, paste, edit labels again, and select all the data set, clicking in the crossing here. Multivar, principal components. Here is the percentage of variance, unstandardized, really non-standardized matrix, but please remember to use the correlation matrix, so the standardized one. You can observe that from 97 of the first axis, it reduced to 43%. So it lose a lot of information on the first axis, but is a good loss because you avoid the magnitude of the variables. So you are independent from the magnitude of the variables. So correlation, then you scatter here. If you want, we can also color with different colors the different horticultural species. So close this, and this is the way of past of evidencing groups. This could be used for unsupervised techniques such as PCA or the other ordination techniques that we observe today, but could be used also for the discriminant analysis, so the supervised techniques. So to color, so to show the different groups, you have to select the first group in this way. So you have to click on the first label, move on the last observation of the first label, press on your press shift and click. So the first group is evidenced. Go to edit, row color symbol here, and give a color, for example, cross red. Again, for the second group, click on the first of the second group, move with the mouse on the last observation of the first group, shift and click. Blue. First, move, shift and click. Pink. Click on the first, move on the last, shift and click. Green. Click on the first, move on the last, shift and click. Okay, and I've lost that. Here we are. And go on with Susina here. Shift and click. We could do it brown. And the last could be without a color because it's black, is the first one, black. So once we have colored all the groups, we can again select all the data set, multivar, principal components, correlation, use scatter, and we can observe that the dots are different in shape. Here is blue plus squares, but also in the colors. And we can also remove the row labels and use the convex hulls, for example. Convex hulls, I remember you, that is the perimeter enclosing all the observation of a group. Or you can use the 95% ellipsis. So not so good. Why? Okay. Okay, so we can use convex hulls and row labels here. So we can observe here the distribution without showing at first the loading, so the variables. So we have the observation of small tomatoes, pomodorino, susina here, the salads, romana, and the trocadero here. Here we have the nectarine, the peaches, and also zucchini here. But why they are positioned in that way? So B-plot. B-plot, we can say that here we have the A coordinates, that mean the reddish colored fruits, horticultural products. So here, of course, we have tomatoes and also peaches. And here we have the green one on the opposite side. So higher values of A, lower values of A. On the other side here, we have the tougher, so the most tough here, and the tender here. Okay. And also here on the first axis, we have the weight. So salads are much more heavy than small tomatoes. And this is the meaning of this plot. Okay. Now I would like to show an example from Excalibur, at least. So this is a course on soil samples, so we have to use also examples from soil. So let's see, first of all, the chemical, on the chemical database from the initial status of Excalibur dataset. So we can open chemical XLS here. Okay, so here we have different variables evidencing the different groups. So we have the crop, the type of crop. Here we have tomato with T, S is apple with A, and S is strawberry. The management method is intensive or organic, I believe. The condition is field and greenhouse. The treatment, I can't remember the codes, and the different partners of that provided the data, and also the environmental zone, so Atlantic, continental, etc., etc. So let's try to perform a PCA using, for example, we can do the environmental zone. Okay, so and here is the variable, sorry, pH, pK, calcium, magnesium, etc., etc. So this is the chemical variables that we used. So we can copy this data set from the column N here, copy, go on past, file, new, okay, edit labels, go on the crossing on the top left, and paste here, edit labels, okay. So here we have all the data set positioned with the labels of the rows and of the variables of the columns. Select all by clicking on the upper left crossing here. Multivar, principal components, correlation, please remember, use scatter. Okay. So here we have the plot, but we can say that this plot is characterized by sandy with observation with much more sand, a higher value of sand here from that side, that observation here, and lower values of silt and clay from that side. From the opposite side, of course, we will have higher values of silt and clay here, and lower values of sand from that side. Let's see the second component, so from up to down. So this point, of course, is characterized by higher values of K and P, and most of all higher values, because this value of mg is quite low in terms in absolute terms, so it's less than 2, while here we have more than 3. So here we have higher values of K and P, and here we have lower values of K and P. I would like to show you how to prepare to use Excel for the plot. I think this could be useful for you. So first of all, from the software that you are using to perform the analysis, you have to import the data. So here simply you can copy and paste values here. Okay, this is the way of importing data from past. So you have the explained variance here. Then you can go to new scatter here, new numbers, copy, and paste here. It's quite different, but because this is the partner code, so we can use the partner code is here. So we have the coordinates here, and the same from new loadings. The numbers, copy and paste. So while it is easy to plot the coordinates of the scores, that is these two columns, it could be quite complicated to find a way of plotting the vectors. How to do this? This is a method that I invented, we could say. So here we have the data directly from past. You have to put the data, copy the data in another part of the data set here. And then you have to alternate the coordinate of a variable with zeros. So 0, 0, 0, 0, and put one to another. How to do this? I do in that way. Here is 1, 3, and so, okay, and 2, 4 tail numbers. Here, I arrive until 16 here, and order and sort in that way. Okay, so this is the output in that way. But if you plot this output, the vectors are very, very small. So we have to multiply these values by a constant, for example, 6. So here in this formula, you have this value multiplied per this constant here. And if you see, if you change here 5, it reduces, the vector's length is reduced for one very, very short. Okay, so you have to find a way of representing the number where you can represent both coordinates and the vectors in order to be visible. So I find that 6 is a good approximation of this. And here you can interpret data. Before we have seen on the environmental condition, now we can see on the partner code, we have CRP from that side, only that side, etc., etc. So it was just to show you that example on soil data. So let's see another example. Microflora NGS dataset. Ordination. Okay. So this is a larger dataset. We can, which kind of, okay, we can use F is the condition. We can use the condition factor to perform a PCA considering the condition factor. So, or we move this variable here, side here, and we can copy all the data set in the same way as before. Okay. Copy. File new. Okay. Edit labels. See. Okay. And here we have, of course, different kind of variables. So we have diversity indexes. So richness, Shannon, Simpson for 16S, etc., etc. So it's different kind of variables with also different kind of magnitude. So richness 16S as hundreds in terms of magnitude, while here we have unit magnitude, and so it is much more important to remember to standardize. So we can also maybe, yes, color the two groups. First group, click on the first row of the first group, move on the last of the first group, shift and click. Edit row color symbol. Okay, what is it? Edit row color symbol. Okay, and red. The other one, we have two groups. So in field and greenhouse. So F in field is red and G greenhouse is black. We select all the variables in that way, click in the crossing here. Multivar, principal components, correlation, view scatter. Okay. What? Is there a question? We can observe the convex hulls here. Or, I don't know why the ellipsis doesn't work well. Maybe, yes, I understand. Because the font is too large. Maybe. No. Don't know why. No. Don't know why. However, without ellipses, okay. We can observe that in general, G values are positioned much more on the negative side of the first axis, having lower values of all the variables, while these, most of all, field values showed higher values of these diversity indexes. And this is a result that should be interpreted by someone that then I'm not an expert of soil biodiversity, but I can support with graphical with the statistics for the correct interpretation of data. Okay, so I believe that we have quite well, I hope we have quite well understand how to perform a PCA. As you have seen, is quite also fast to perform this analysis on past, but also on the software that you usually use. Okay, so we can continue with other kind of ordination techniques. The second ordination techniques that we will observe is the correspondence analysis. This analysis follows a unimodal model of observation that are expressed as discrete values of reported as frequencies. The correspondent analysis searches for the internal and unobservable structure of relationship between variable and object. So while in a PCA we observed in the B plot the scores, so the coordinates of the observation, and the variables represented as vectors, but not staying in the same space, with the correspondence analysis, we have a correspondence. From this comes the name of this analysis, a correspondence between observation, so the rows, and the columns, so the variables. And we can discuss these results in that way. So there is a correspondence here from that points of sampling points and the species, and so a correspondence between these species that are positioned here in the same space with the sampling points. And so it allows to represent simultaneously and in the same space point variables and points of observation with a distributional equivalence. Okay. Due to the type of input data, we can have analysis of correspondence or simple correspondence on qualitative data, or multiple correspondence analysis with mixed data, where in the second case, the quantitative analysis must be transformed into classes, into qualitative data. So, for example, for class 1, weight lower than 2,000 grams or higher than 2,000 grams. And so the matrix should be transformed in an intermediate matrix that is named complete disjunctive of presence and absence, similar to a transformation in dummy variables. Here is an example of an ordination a complete disjunctive matrix. Here we have the time 0, 1, 2, 3 and the single observation, and 1 or 0 if it's time 0, 1, 2, 3, etc. The year, the Brix degrees, the days from the harvest, the weight, etc., etc. So this is a 1-0 analysis matrix. Just a moment. Okay. The analysis continues with the extraction of the BART table that reproduces the submatrices, so that extract is a synthesis of the observation of a group. In past, you have to import the BART table. Let's see directly on the file ordination techniques, the sheet correspondence analysis. Okay, ordination techniques, correspondence. So this is the original matrix. That way, we have different cultivars, different timings, years, Brix, etc. This is transformed in the complete disjunctive matrix with 1 and 0, and using a simple pivot table, we have the summary. So we sum here Gallo C have at T0, 1, 2, and 3 observations. So here we have 3, etc., etc. So this pivot table is the BART table useful to be exported in past. So copy here, file new, okay, edit labels, add the crossing on the upper. So here we can paste and again edit labels. Select all the matrix, multivar, correspondence. Here is this new multivariate ordination technique. Here we have the eigenvalues, because also corresponding analysis is based on eigenvalues and eigenvector, and also we have the percentage of explained variance here, as before, for PCA. View scatter. We can represent the row labels. I can enlarge the. Okay. So here we have the different cultivars here, but we can also represent in the same space the variables and the labels of the variables. So, and we have to observe because, for example, okay, Brix low and Brix high. So from Brix low to Brix high, here we have the cultivars with higher Brix values. Okay, and Lemso, these two cultivars have lower Brix values, etc., etc. So it's similar, but the points are in the same space, and most of all is based on qualitative variables, not quantitative. Okay, let's go on. Here is an example, a very particular, special example of the corresponding analysis that in Italy, for example, happens also in the real life, not only for research. Here we have an example that during election days, it works to show you which party you are most similar. So you can put your just to show you, I put something in by chance. Okay, okay, just to show you the result. There is a correspondence analysis. Okay. Magari. Ok. Okay. Okay. I'm positioned wrongly, of course. Here, so close to Berlusconi and Meloni, etc., etc. And this is a correspondence analysis. So my new input is positioned here. Maybe one thing that I didn't said you on the PCA is that if on a PCA matrix you add one row, the ordination could completely change because it depends on all the matrices. Okay, so let's go on with the principal coordinates analysis. The principal coordinates analysis generates an ordering of object by extracting eigenvalues and corresponding eigenvector, but from a matrix of distances between objects. So generally it uses Euclidean distances and Gower index. And it is used when a PCA could not be applied. Now we can pass to the techniques that use the two blocks. This is a special family of techniques, of ordination techniques, because in that cases you have two different blocks of variables. In particular, in general, most often, you can have an environmental variable and, for example, a list of species or other kind of variables that could be, don't know, morphometric or diversity indices or whatever. We show in specific with the example from Excalibur, the canonical correspondence analysis, the canonical. But I'll show you also something on the non-metric multidimensional scaling and the two-block partial least square. The non-metric multidimensional scaling aim to obtain an order of object that preserves the order, so the rank of the original distances. So it is used in specific cases. I will show here that in this case the plot is based on observations, the same as PCA, correspondence analysis, etc. You have the point of corresponding to the environmental data in the same space, and the vectors representing the other block. So in this case is a spectral values. Another analysis is the two-block partial least square. This is developed by Rolf and Corti on 2000. It's a quite recent ordination, and is based on PLS. That could be similar to PCA, but using latent vectors that are different from principal component axis. As before, usually the first block concern environmental variable, and the other one, as we said before, could be morphometric variables or other kind of variables. In this case, the analysis apply the PLS differently on the two matrices, so the two blocks. So this is the values of the first axis for block 1, and this is the values of the first axis on the block 2, so differently. The analysis seems to work well if the observations are positioned on the bisectrix of this graph. So in this case, it's quite well positioned. And you can observe the contribute, so the loadings, such as on the PCA, of on the first block and on the second block. Here we had the box of the analysis of box on the grain, I believe it was grain, and the presence of mycotoxins, different kind of mycotoxins. And we observed that here, so lower values, we had these mycotoxins here, that is related with this kind of box. So there is an association here. So two blocks analyzed differently and compared on the same graph, extracting the contribute on the two of the variables of the two blocks. Let's arrive to the last, but not least, analysis. That is the canonical correlation analysis, named Canonical. The aim is to identify the linear relationship between two groups of quantitative variables observed on the same set of individuals. The same as before, so the same observations, two groups, two blocks of variables. And as for the non-metric multidimensional scaling, we have the observations and the variable in the same space and the vectors of the other block. Let's try with two examples for the Canonical. If you want, if you have time, we can also observe the same data set using multidimensional scaling and to block PLS. That is quite similar. So environmental, chemical, microfauna database. So microfauna, here we are. Here we have the variable the factors here, and the two blocks of variables. So here we have the environmental and the chemical against the second block. This is the microfauna, so the nematodes expressed in different way. I'm not an expert of this. So we have to remember how many variables we have in the first block. Let's count. And so 15 variables against 15 against 5. Okay, so a total of 20. We would like to observe the partner code. So we move this column goes to the data set. Okay, and copy all the data set. Okay, file new. Edit labels. Edit labels again. Select all the columns. Multivariate. So here we have the non-metric multidimensional scaling, the two-block PLS, and the canonical correspondence. Let's start with the canonical correspondence. Would you see here, the software asks you the number of columns of environmental variables. With environmental variables, he means the first group, so you have to put 15. So there is the first group and the second group. The first group have 15 variables. Okay. Allora, so here we have the observation, the rows here. Okay. So the rows here. We can observe CRP from that side, ENH from that side, TUG from that side, OA is here, etc., etc. The contribute of the first block labels, okay. We can also plot the dots, but also only plot the labels here. So this is the second block represented as points in the same space. Okay. So here we have that in that part, so CRP have higher values of that side, while NEM TN has lower side in CRP, but higher in TUG, for example. And also we can do the same observation as we did for the PCA. But also the tree plot. Okay, here is the loadings, so expressed as vectors of the first block, so the environmental and chemical variables. We can augment with the tree plot length in order to better observe the variable in that, part. So we can say that CRP is characterized not only by higher value of NEM-PF, but also mean year temperature higher than 20 degrees, clay, and lower values of sand, for example. Here, TUG with higher values of PK and CA, and lower values of clay and mean, etc. This is the way of representing that. As for the PCA, it is possible in the same way to represent the tree plot also in Excel using the vectors as before. So different colors, different kind of graph, but very easy. Sometimes it is useful to represent, the graph not all together, especially if you have many points. So you can represent, for example, this graph here and this other here. So with the two blocks or in that way. So couple of kind of information. So scores, first block vectors, and second blocks scores in the same way. Okay, just a quick observation on the same data set for the two block PLS, always 15, first block 15. Correlation, we have to standardize as for the PCA. View scores, quite well positioned, if you scattered, but however, quite positioned on a principal bisectrix here. So the first block, first axis here, and first block, no, second block, first axis. here. But most important, let's see the loadings. So here is the loadings of the first block, first axis. So here we have higher values of mean, this one here, and clay, and lower values of sand. And from that side, lower values of clay and mean, blah, 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 and higher values of clay associated with the second block, that side NEM PF and lower values of NEM VA, and that side higher values of NEM VA, and of course these results converge with the Canopy ones, but it depends the way of representing and how you want to discuss the results. Just a quick, in the last couple of minutes, just a quick view of non-metric multidimensional scaling, always 15 on the first block. And here you have to select this similarity measure, so the distance measure in particular. We always use Euclidean distance. So as you can see, row labels, so the observations, and as vectors, you can observe the variable here, but not the second block, because the second block is used to obtain the graph, so it's not plotted. Let's see, the three-dimensional. No, it doesn't. Okay. Okay. Are you still alive? So I think that we are approaching to the end. So if there are any questions, I'm here. Or otherwise, we can see you tomorrow at the same hour. Let's stop the registration.